On November 14th, astronomers captured hauntingly anomalous images of ThreeI Atlast. ThreeI Atlast exhibits a massive jet structure, including 2 anti-tail jets and a main tail stretching millions of kilometers, vastly larger than any typical comet. Scientists are analyzing the data because the enormous mass loss rate required to sustain these jets, along with the sudden appearance of 7 distinct jets near perihelion, does not align with conventional natural comet models. This chain of anomalies has sparked fierce debate among space agencies. Some data has been suppressed. The scientific community is divided between the hypothesis of an ultra-anomalous comet and the possibility that Atlast is a designed system, a vehicle, a remnant, or a non-passive interstellar entity, suggesting that we may have just passed the trace of an intelligence we were never prepared to encounter. Right now, we join the astronomy community in the latest and unprecedented investigation of ThreeI Atlast to explore its shape structure and a sequence of mysterious behaviours, as if being controlled by some distant force. At exactly 04:13 Coordinated Universal Time, a low-gain data stream from the Neowise survey picked up a reflection, just another icy wanderer catalogued like the thousands before it, except this one pulsed. The return curve wasn't noisy or erratic like a typical comet tail, it oscillated with unnatural symmetry. Even more unsettling, the brightness modulations appeared on a fixed interval every 11:26 minutes. ThreeI Atlast had just entered the sensor range beyond the orbit of Jupiter. It shouldn't have shown this level of activity. No comet this distant 5.2 AU away has ever spontaneously brightened in such a smooth, consistent manner. There were no signs of rotational precession, no gas jets, no grain fragmentation models that fit. So the question formed quietly in the dark. What kind of natural object emits a rhythmic high-contrast light pulse, like a controlled beacon? The analysis team flagged it as a probable instrument error, but ThreeI Atlast didn't go away. It kept pulsing, every 11:26 minutes, without fail, and for the first time a veteran observer muttered aloud, "This isn't debris, it's trying to be seen." The light curve from ThreeI Atlast suggested a reflective surface area far larger than the initial projections. Not just a dusty coma or active jets. Something massive was interacting with sunlight and doing it cleanly. Standard albedo models pointed to a body at least 6 kilometers wide, but infrared readings from the Subaru telescope in Hawaii contradicted that. The heat signature was faint, far too low for an object of that size. This posed a stark contradiction. Either ThreeI Atlast was far smaller than it appeared, or it was reflecting light at an efficiency no comet had ever demonstrated. When astronomers simulated the mass loss rates required to generate such a high-intensity photometric flare, they hit a wall. A comet that bright should be disintegrating, but ThreeI Atlast showed no signs of surface shedding, no cloud diffusion, no fragmentation tails. If it wasn't shedding mass, if it wasn't hot, then why was it so bright? Something was amplifying its visual cross-section, not physically, but optically, like a surface shaped to reflect, or worse, engineered to confuse. ThreeI Atlast had just violated the size-to-signal ratio, and no one could explain how. ThreeI Atlast was supposed to behave like a comet. That meant volatile-driven activity governed by solar proximity thermal lag and mass-shedding models. But ThreeI Atlast broke every one of those rules. At 5.2 AU, any water ice should have been dormant. Sublimation rates this far from the Sun were negligible, barely enough to lift dust from the surface, and yet the object exhibited a steady non-random acceleration completely detached from solar wind variation. Jetting was ruled out. Spectral signatures showed no signs of CO2 or CN plumes, the typical fingerprints of deep space activity. The trajectory shift of ThreeI Atlast, though subtle, did not align with any known outgassing vectors. When plotted backward, the anomalous motion appeared to begin before perihelion, before it was even close enough to be thermally triggered. Physicists in 2 independent labs attempted to model the thrust using dust grain ejection dynamics. The math failed. Not slightly catastrophically. The expected ejection angles would require surface vents larger than the body itself. That left one conclusion. Either the comet's physics were wrong, or ThreeI Atlast wasn't a comet. And the deeper question lingered, was this the start of a new category or the end of our current model? Comets don't fight solar wind. They dance with it, swept, pulled and reshaped by plasma streams flowing outward from the Sun at 400 to 800 kilometers per second. But ThreeI Atlast didn't behave like a passive traveller. When observed through ESA's solar orbiter coronagraph, the tail of ThreeI Atlast displayed a stubborn, almost defiant curve arcing against the wind vector. Instead of flowing radially away from the sun, the tail bent at a 38-degree offset. That's not normal, that's reactive. Solar wind pressure should have pushed its ion tail into alignment, yet ThreeI Atlast held formation. It was as if something was maintaining orientation, actively adjusting. Magnetic interference was ruled out. There was no recorded coronal mass ejection during the anomaly. The solar conditions were quiet. Too quiet for chaos. So how did ThreeI Atlast resist no known material configuration or mass loading explains this level of deflection at that distance? Unless, of course, it wasn't reacting to the wind. It was ignoring it, or shielding from it. Whatever was happening, ThreeI Atlast had just demonstrated intent, or at least the illusion of it. The Lowell Observatory flagged something alarming. The brightness of ThreeI Atlast had dropped by nearly 1.2 magnitudes in just 72 hours. That's equivalent to losing over 60% of its visible surface scattering power. Naturally, astronomers suspected a fragmentation event. That's common for dynamically new comets entering the inner solar system. But the debris field, it never came. No dust plume, no secondary body, just less. Spectral backscatter suggested a dramatic decrease in mass but with no outward ejection signature. The coma faded, yet no particles were detected in follow-up polarization sweeps. ThreeI Atlast had lost mass without leaving a trace. Models from ESA's finite mass flux array estimated a material deficit equivalent to 4.2109 kilo. That's more than a small mountain. Gone. Disintegrated, vaporized, no. Just disappeared. The only analogy that fit involved artificial cloaking via phase angle redirection, a concept theoretical at best. So the question hardened. What kind of object loses mass silently without thermal flare debris field or recoil? ThreeI Atlast wasn't crumbling. It was slipping away, and we weren't allowed to see how. In Comet, physics survival isn't subjective, it's math. Any object approaching the inner solar system must withstand extreme tidal forces, thermal gradients, and solar radiation pressure. There is a threshold, a minimum structural integrity linked to size and material cohesion. Drop below that, and sublimation becomes self-destruction. According to NASA's resilience curve for a comet to survive past 2 AU without catastrophic shedding, it must retain a core of at least 1.4 kilometers in diameter. And yet, ThreeI Atlast's post-perihelion estimates suggested something far smaller. Revised models based on reflected light and coma density pointed to an active core no larger than 520 meters. That's nearly 1/3 of the minimum. Worse, its albedo, the measure of surface reflectivity, had increased. Instead of darkening like a typical carbon-rich nucleus, ThreeI Atlast appeared cleaner, shinier, as if it had been scrubbed or replaced. So how did it survive? How did ThreeI Atlast defy structural fragmentation? Thresholds maintain trajectory and keep accelerating. One idea surfaced: shielding, an exolayer of artificial material capable of heat diffusion and torque compensation. But that would imply design, not randomness, and once again the unsettling thought returned. Was ThreeI Atlast playing by rules we hadn't written? In early November, astronomers expected a show. ThreeI Atlast was descending fast toward perihelion, its closest approach to the Sun. Historically, this is when comets ignite. Sublimation peaks, jets erupt, tails unfurl, but not this time. Instead of a photometric surge, ThreeI Atlast dimmed. Instead of explosive outgassing, it stabilized. And then, silence. All sky systems in Hawaii and Chile picked up a subtle anomaly. The object's light curve flattened. No flickering, no phase lag, just an eerie uniformity. Thermal infrared scans from ESA's ground array returned another surprise: surface temperature dropped by 11.6 degrees, even as solar proximity increased. That shouldn't happen. Unless energy was being managed, stored, redirected. Was ThreeI Atlast entering a passive mode, or worse, a premeditated state change? For an object under solar assault, this wasn't survival. It was orchestration, and with perihelion just days away, Earth would lose direct line of sight. Exactly when ThreeI Atlast stopped pretending to be a comet. When ThreeI Atlast re-emerged from behind the Sun, it was different. Not fragmented, not fading, amplified. NASA's Stereo A coronagraph caught the first pulse, a burst of luminosity nearly 17 times its baseline output. but there was no fan-shaped ejector, no chaotic dust halo, just a sharply defined coma unnaturally symmetrical. This wasn't outgassing, it was emission, and it followed a rhythm. Amateur astronomers in New Mexico recorded optical flashes at 6-minute intervals, consistent pulsed and strangely monochromatic. Even more bizarre, its trajectory didn't alter. Comets usually stagger after an outburst, but Atlast kept its path. Clean, unperturbed. Spectrographs revealed a sharp spike in exotic ion signatures, including nickel ions, typically seen only in solar flares. Where did that energy come from? The timing was surgical, the release contained, the symmetry deliberate. ThreeI Atlast had crossed its solar trail not weakened but activated, as if it had used the sun not to survive but to awaken. And for the first time, scientists whispered what no one dared before. What if this was intentional? The first official response came swiftly. NASA's Minor Planet Center issued a bulletin outburst consistent with delayed volatile release. In simpler terms, a classic cometary outgassing event. The theory went like this. As ThreeI Atlast neared the sun, subsurface ices remained insulated. Then once enough heat-penetrated deep layers, pressure built. A rupture, a burst, a flare of gas and dust. Case closed, except it didn't match. The thermal profile from James Webb showed uniform surface cooling, not the localized heat spikes expected before rupture. Spectral lines lacked carbon-based volatiles common in icy comets. Even the coma's geometry betrayed the theory perfectly concentric, uncharacteristically stable. Most damning of all, no spin alteration. For a comet to eject mass with such force and not alter angular momentum, it bordered on impossible. The sublimation hypothesis calmed the press. But within astrophysics circles, doubts festered. This wasn't textbook behavior. It was too clean, too symmetrical, too coordinated. As one ESA mission director put it, if this is a comet, it's one that read the manual and decided to rewrite it. ThreeI Atlast didn't just survive perihelion, it maneuvered through it. That was the claim. Quiet at first, whispered in late-night academic chat rooms, encoded in footnotes, but it grew, louder, bolder. In October, trajectory analysts at ESA flagged a pattern micro-adjustments in Atlast's arc. Tiny course corrections measured in arc seconds executed without apparent cause. No jets, no torque, no delay. Simultaneously, NASA's Deep Space Network registered residual energy emissions trailing Atlast in rhythmic pulses, 7.4-minute intervals, regular, consistent. Deliberate one hypothesis emerged. A non-gravitational propulsion system not based on ejection of mass but radiation control. Specifically photon pressure modulation. By dynamically altering surface albedo across precise vectors, Atlast could exploit solar radiation itself to generate thrust. No fuel, just intention. Such maneuvering isn't impossible. In fact, humans have tested similar concepts, solar sails, Yarkovsky effect amplifiers. But to see it on a body this size, unprecedented. If Atlast was controlling its path that rewrote the equation entirely, it would mean it understood stellar dynamics. It would mean it chose its entry vector, its perihelion approach, its reveal. And most disturbingly, it would imply that ThreeI Atlast had somewhere it was trying to go. Not a comet, not a fragment, a vehicle. In the days following perihelion, Atlast should have stabilized, but instead it became more complicated. Hubble's post-perihelion imaging revealed layered ejector trails, not radial but interlaced, not diffuse but threaded like woven fibers of dust and metal. Astronomers struggled to model the pattern. The emission vectors were too ordered, almost architectural. Each wave seemed to echo the one before it, not chaotic but sequenced. Then came the spectral anomaly, a signature spike in nickel ion blends laced with trace amounts of tungsten and molybdenum, elements common in aerospace alloys, rare in comets, rare even in meteorites. ThreeI Atlast wasn't disintegrating, it was disclosing. Infrared data from JWST captured heat signatures from the core, but they didn't fade. Instead, they pulsed every 93 seconds, mimicking a cooling regulation cycle, a loop, a breath. The object no longer behaved like an ice rock swept by solar forces. It behaved like a system, one balancing thermal output, one correcting course drift. In every sense, measurable ThreeI Atlast acted like it was still operational. When Atlast's core signature started to shift, fragmentation became the leading theory. Telescopes worldwide captured a growing spread, a fanned-out dispersion pattern that looked eerily familiar, multiple subnuclei breaking away. That's how natural comets die. Stress from solar heating causes the body to crack, exposing fresh volatile surfaces. Eruptions follow, dust increases, and the comet loses cohesion. Eventually it crumbles. But Atlas didn't follow that script. Yes, the debris field expanded. Yes, multiple echoes appeared in the coronagraph frames. But the fragments were too symmetrical, spaced at near equal angular intervals. 6 substructures, each reflecting light in rhythm, emerged like petals opening from a mechanical bud. This wasn't collapse, it was deployment. Instead of disintegration chaos, the surrounding shell appeared to self-arrange. Infrared imaging revealed maintained thermal levels across all pieces, not a single dead core. Even stranger, the fragments realigned themselves every 47 minutes. That's not how debris behaves, it's how satellites orbit a hub. Some astronomers called it coincidence. Others called it an operating system with modules. A few simply refused to speculate at all. But the fragmentation hypothesis, while comforting, now demanded too many exceptions to fit. Because if Atlas truly fragmented, why did the pieces stay warm? Why did they retain angular velocity? Why did they respond to solar changes as one unit? The pieces didn't fall apart. They might have fallen into place. When Atlas passed perihelion, the comet's path didn't just bend, it curved deliberately. Trajectory simulations run by ESA and JPL had accounted for solar radiation pressure, outgassing vectors, and gravitational harmonics. Yet the post-perihelion arc was too tight, the velocity shift too sharp, and the alignment with Venus's orbital plane too perfect. What force acted on Atlas at that exact moment? The natural explanation pointed to jetting volatile ices sublimating and creating reactive thrust, but the timing, precision, and consistency of the deflection didn't match known physics of chaotic cometary jets. A team at Kyoto University modelled an alternate system, directed propulsion via embedded vent arrays. By releasing mass along a programmable pattern, a craft could steer without leaving ion trails or visible gas emissions. It would resemble a comet to observers and yet move like a ship. That model, when applied to Atlas, matched 93% of the real trajectory. NASA dismissed it as an interesting but unnecessary complication, but other analysts weren't so quick to ignore it. James Webb's thermal mapping showed that the brightening after perihelion was not random, it migrated clockwise along the object's long axis. It's as if Atlas had activated specific surfaces in sequence, achieving rotational control. Most comets spin out of control as they heat. Atlas didn't spin, it steered. If true, this wouldn't just challenge comet science, it would imply intentionality. Something guiding the mass ejection. Something navigating solar vectors. Not a reaction, a maneuver. The mass of Atlas never quite made sense. Initial estimates derived from coma expansion and light curve dampening suggested a nucleus of roughly 700 meters, a relatively standard size until it wasn't. Post-perihelion observations from both SOHO and the Daniel K. Inouye Solar Telescope revealed something staggering. Despite shedding what should have been tens of millions of tons of volatile material, Atlas's core structure remained intact. Not just intact, stable, undiminished, and moving with more control than before. How could it lose mass and yet behave as if it hadn't? Mass loss curves tracked by ESA's CAM system revealed a critical inconsistency. Gas and dust ejection rates were 3 to 5 times higher than standard cometary baselines. Yet the gravitational binding of Atlas did not weaken. Its tumble rate did not accelerate, and its outgassing never appeared to produce significant reactive force. This pointed to a possibility no one wanted to say out loud: the visible dust and gas weren't coming from the main body. Instead, they could be decoys ejected from shell fragments, smaller bodies designed to simulate mass shedding. Fragments that orbit and mimic evaporation while leaving the core mass untouched. Japanese radar teams tried to locate those decoupled fragments using polarized scatter. They found something stranger: layers, multiple concentric layers within the coma, like onion skins. Engineered shells. This led to a wild but rising theory. Atlas might not be a single mass at all, it might be modular, like a cluster payload discarding outer sections one by one under the illusion of cometary erosion. No known comet behaves like this. Even the wildest sungrazers like Comet Lovejoy burn fragments spiral out of coherence, but at last it survived, and in doing so it revealed nothing about what it truly is. Something isn't adding up. Mass is leaving, but mass remains. The numbers are clean. The object is not. From the very beginning, Atlast's orbit refused to obey. When it was first plotted in July 2025, analysts expected a predictable hyperbolic escape, a parabolic swing around the Sun, similar to other long-period or interstellar comets. But Atlast's trajectory never locked. Every recalculation shifted slightly marginally until by August the deviation passed statistical significance. It wasn't a gravitational fluke. NASA's JPL orbit solution Duster 23 showed an outbound vector that had shifted inward as if something had exerted force against the Sun's repulsion. The non-gravitational parameters A1, A2, A3 used to model cometary outgassing effects began to diverge violently from standard expectations. Not one, all three. This was not typical solar wind acceleration. This was not a symmetrical sublimation. This was guidance. The object's orbital arc began aligning with resonant points, Lagrange nodes of Venus and Mars regions of gravitational stability that no natural object traverses in such a clean linear fashion. Then came the Earth approach. On December 19, 2025, Atlas passed within 1.8 AU, just beyond Mars. During this interval, something impossible occurred. Its outbound trajectory bent slightly toward the plane of Earth's orbit. Not enough to cause alarm, but enough to trigger a full anomaly review from the IAON International Asteroid Warning Network. The conclusions inconclusive. The working theory localized outgassing, but there was no observed ejection, no vector-adjusting burst, just a change, quiet, smooth, statistically undeniable. More curious still was the acceleration curve after perihelion. Instead of a slow drift into interstellar space, Atlas accelerated sharply mid-January, as if initiating a burn. Solar radiation pressure can explain some behavior, but not controlled curvature, not frame-to-frame alignment with Venus's orbital path. Was it using planets for momentum, performing a modified Oberth maneuver without thrust? One team from the ESA proposed a chilling alternative. What if Atlas wasn't bound to a single orbit at all? What if it was switching, adjusting, plotting? This would make Atlas not merely a comet, but an adaptive probe, one whose orbital path is not dictated by chance or chemical reactions, but by intent. We're used to celestial mechanics behaving like clockwork, but Atlas behaves like a clockmaker, and the question that now haunts orbital analysts is no longer where did it come from, it's where is it going? Atlas was never just a strange comet, it was a statistical insult, because when researchers tried to calculate the odds of all its anomalous features happening by chance, they didn't just find low probabilities, they found something else, something that defied the entire framework of randomness itself. Let's start with the orbital parameters. ThreeI Atlast passed unnaturally close to the orbital paths of Venus, Earth, Mars and Jupiter, within narrow proximity windows of plus 0.02 AU. That's already odd. But when Dr. Liu from the Tsinghua-NASA collaboration project ran a multivariable Monte Carlo simulation testing 10 million random interstellar objects with similar entry vectors and speed ranges, the results were staggering. Only 1 in 231 Zionid randomly generated trajectories intersected 3 or more planetary orbits within such proximity. None intersected 4, ThreeI Atlast did. But that was just the beginning. Add in the non-gravitational acceleration patterns, the sudden increase in velocity after perihelion without a correlated spike in observed mass loss. Now layer in the minimal coma, the high thermal resilience, the asymmetrical mass shedding, and the directional dust jets with no standard isotropic spread. Each anomaly on its own could perhaps be dismissed. But combined, when Dr. Henrika Volkov of the University of Lund applied a compound probability matrix accounting for the 6 largest anomalies in Atlast's behavior and structure, she found something terrifying. P1 in 3.8 billion. That's less than the odds of being struck by lightning and winning the lottery on the same day repeated 3 times in a row. But it gets worse. When they ran historical comparison models across all known comets observed since 1884 from Halley to Hale-Bopp, none exhibited more than 2 of these anomalies at once. ThreeI Atlast had 6. This leaves us with only 2 statistical possibilities. Either we've encountered the single most anomalous natural object ever observed in the history of astronomy, or it was never natural to begin with. Atlas could be the result of intent, not coincidence. Its trajectory may have been calculated, its thermal shielding designed, its post-perihelion propulsion pre-programmed. Suddenly the question is no longer how this happened, but who wanted it to, and why they wanted us to see it. Because if ThreeI Atlast was placed timed and triggered, then we are not alone, and we were never meant to be. What do you do when probability breaks? When the frameworks built to guard us against fantasy math statistics, scientific conservatism suddenly point toward the fantastical? That's the dilemma ThreeI Atlast left behind. Because once the anomaly probabilities were aggregated, once astrophysicists ran their simulations again and again, a different kind of data began to emerge. Not data that confirmed a hypothesis, but data that violated expectations. Dr. Raphael Conrad, a statistical physicist at the Max Planck Institute, described it best. We weren't looking for patterns, but the numbers kept pointing toward intent. What does that mean? It means the configuration of anomalies on Atlast, orbital proximity, directional dust ejection, thermal irregularities, mass shedding asymmetry, behaved not like outputs of chaos, but like outcomes of constraint. Like something had chosen a path through our solar system that maximized visibility, survivability, and confusion all at once. This doesn't imply intelligent design as a certainty, but it demands that we abandon the assumption of independence. In classical statistics, each anomaly would be treated as a discrete event uncorrelated with others. But what if they weren't? What if the trajectory and the dust jets and the thermal shielding weren't random but linked by design logic? Then the odds no longer matter, because you're no longer rolling dice, you're following instructions. The implication is staggering. It forces the scientific community into a new epistemological space, one where the null hypothesis is no longer natural randomness but non-random assembly, where absence of evidence is not evidence of absence but perhaps intentional masking. In that light, ThreeI Atlast doesn't just challenge astrophysics, it challenges the philosophy of science, and perhaps that was the point. In mid-September, as ThreeI Atlast slipped past the orbit of Mars, the Mars Reconnaissance Orbiter MRO happened to be in a rare favourable alignment. It was a coincidence born of orbital mechanics, and it changed everything. For just a 27-minute window, the MRO's high-rise camera was able to capture high-resolution imaging of Atlast's post-perihelion trajectory from an oblique angle no Earth-based observatory could match. The images were meant to confirm structure loss track dust emission geometry and estimate mass ejection rates. What they revealed was far stranger. Frame-by-frame image stacking showed a consistent asymmetry in Atlast's coma, not just lopsided brightness, but directional curvature almost like a tail being steered. And buried in the far ultraviolet spectrum, an even more perplexing anomaly, micropulses and gas emissions that followed a fixed interval, approximately every 88. 1 second's far too regular for any known sublimation process. That's when the MRO team alerted NASA's Planetary Defense Coordination Office (PDCO). Initial analysis tried to rule out instrumentation error, but 3 independent cross-comparisons with earlier solar and heliospheric observatory ESA coronagraph footage confirmed the pulse timing pattern, faint but present in prior perihelion moments. The conclusion: ThreeI Atlast had been emitting periodic microjets both before and after its closest approach to the Sun. But that wasn't the most shocking part. The direction of these jets didn't align with natural spin axis vectors. They were subtly offset, almost as if they were being oriented. This led to a heated debate at the European Space Agency. Were these jets a kind of thermal regulation artifact, or did they constitute rudimentary propulsion? If the latter, it would imply control, intent, function. The MRO data, when reprocessed using temporal brightness subtraction filters, showed further fragmentation events occurring in sync, with jet bursts, suggesting not just propulsion, but maneuvering through controlled loss. To be clear, there is no confirmed detection of artificial hardware, no metal signatures, no structural components, only motion, only behaviour. But sometimes, in the absence of visible machinery, motion becomes the message. ThreeI Atlast may have spoken not through light but through trajectory. An MRO may have captured the moment it whispered back. The data was clear, the timing was urgent, and yet nothing moved. Despite MRO's unprecedented findings, the internal response at both NASA and ESA was stifled by something colder than doubt bureaucracy. According to internal memos later leaked to an anonymous astronomy forum, the Planetary Defense Coordination Office (PDCO), had flagged the ThreeI Atlast anomaly as a potential controlled object as early as October 2nd, but the phrasing was softened, downgraded from requires immediate coordination to pending further review. Why? Because activating an international alert system, particularly one involving language like intentional motion or non-natural periodicity, would trigger global protocols under Article 9 of the UN Outer Space Treaty. Such language had to be approved not just by scientists but by diplomats, national security officials, and in at least one case, military observers. The stakes weren't merely academic. If Atlast was even possibly artificial, it crossed from the domain of astronomy into geopolitics. Worse still, there were whispers of information silos being erected. The James Webb Space Telescope, which had also recorded unusual spectral flickers near Atlast's path, had not publicly released any of its September data despite pressure from multiple observatories. An internal document from the ESA's mission control hinted at interagency friction regarding characterization thresholds. Translation: the US and Europe couldn't agree on what they were seeing or how much to tell the public. Meanwhile, China's lunar ground station claimed it had intercepted telemetry fluctuations consistent with long-period propulsion cycling. But without external validation, their claims were dismissed as speculative. Within weeks, silence hardened into deadlock. No press conference, no collaborative reports, only a slow drip of redacted findings and vague media statements about anomalous but likely natural phenomena. Behind closed doors, the debate split into two camps. Camp A insisted ThreeI Atlast was an ultra-fragile natural comet, simply reacting to solar wind and tidal stress in ways we didn't yet model well. Camp B believed the data demanded reclassification not as proof of alien craft, but as an unknown intelligent origin hypothesis candidate. But Camp B didn't have the votes, not in NASA, not in ESA, and certainly not in the UN Office for Outer Space Affairs. So the data sat, and so did the world watching, wondering, waiting. The comet moved on, and humanity looked away, for now. They weren't supposed to notice, but they did. On October 9th, an amateur astronomer in northern Italy streaming a telescope feed to a Reddit science forum caught what appeared to be a synchronized directional flare from ThreeI Atlast hours after it had passed behind the sun. The data wasn't crystal clear, but it was timed. A 7-second burst. Pause. Another 7 seconds. Then nothing. Within hours, the forum exploded with speculation. Could this be an intentional signal? A spin maneuver? A course correction? What followed was an unprecedented public escalation. Civilians weren't just theorizing, they were coordinating. By October 12th, over 300 private observatories across 27 countries had pooled their data into a decentralized repository called Open Comet Watch, demanding full release of spectral and trajectory data from government agencies. A petition on change.org titled "Tell Us the Truth About ThreeI Atlast" gained 5.2 million signatures in 48 hours. But the real rupture came from within. Dr. Melissa Coe, a propulsion physicist embedded at ESA's Orbital Mechanics Unit, broke protocol and published a paper on ARSIV titled "Re-evaluation of Non-Gravitational Acceleration in ThreeI 2025 A1 Constraints and Implications." In it, she argued that Atlast's trajectory shifts were not only non-random, but statistically synchronized with Earth-Venus transfer windows. She closed the paper with a simple, chilling line: "We're not alone in this trajectory." NASA responded not with a rebuttal, but with silence. ESA issued a formal disciplinary warning to Dr. Coe, and the Archive paper disappeared within 36 hours. But it was too late. Screenshots circulated, mirror copies went viral, hashtags like seconds of Free the Trajectory and Atlast Signal trended globally. Meanwhile, public pressure reached Capitol Hill. A bipartisan letter from 6 US senators demanded immediate declassification of all orbital tracking and thermal imaging related to ThreeI Atlast. One senator even called for a special hearing under the Senate Intelligence Committee, but pushback came fast. The White House issued a statement emphasizing the importance of scientific integrity and avoiding the spread of unfounded extraterrestrial theories. The United Nations Office for Outer Space Affairs warned that premature public interpretation may lead to unnecessary panic. And so, the standoff deepened. Scientists were cornered between NDAs and conscience. Civilians were suspended between fragments of truth and waves of disinformation. And at last, it continued silent, distant, and undeniably watched. The world now demanded clarity. But clarity, as history would soon show, always comes at a cost. It was never just a flyby. On December 8, 2025, ThreeI Atlast completed what astronomers had been calling a routine perihelic maneuver, a close pass by the Sun. But hidden in the geometry of that trajectory was a shadowed truth, a pattern that would only become clear when viewed from one very specific angle: Venus. From Earth, Atlast's path looked like a fading arc. From Mars, it was a speck drifting into twilight. But from the Venusian orbital plane, precisely 44 hours after perihelion, Atlast emerged into full solar reflection at a perfect 26.3° solar elongation, and for exactly 9 minutes its surface flared with unnatural brightness. 9 minutes. 9 times longer than any expected phase angle reflection from an icy or carbon-rich body of that size. The James Webb Space Telescope, repositioned for this moment, captured infrared signatures that didn't match any known natural comet composition. There were spikes, high-frequency thermal emissions rhythmic pulsed at point-and-note intervals. Not random, not chaotic, deliberate. What's more, orbital analysis revealed something else. The path ThreeI Atlast took during this phase was a gravity-assist trajectory consistent with an Oberth maneuver, but not one optimized for escape. Instead, it looped back toward the inner solar system at a vector that aligned not with Earth, but with Venus, and the alignment was nearly perfect. A rendezvous corridor opening once every 11.6 years, where a small object, if timed precisely, could slow itself using the planet's gravitational drag and enter long-term orbital stasis. The odds of this being accidental, less than 0.031%. That figure changed everything. It transformed Atlast from curiosity to a strategic vehicle, because Venus isn't just any planet. It's Earth's twin. Its atmosphere is thick, hostile, and natural shield. Radar visibility from Earth-based systems is limited to short windows, and perhaps most importantly, Venus sits on the blind side of Earth for nearly 40% of each year. If you wanted to park something quietly indefinitely, Venus is your shadow. Dr. Adrian Holt from ESA's Trajectory Analytics Group was one of the first to speak openly. It's not about where Atlas came from, it's about where it chose to stop. Following this event, observatories began rerunning thermal simulations. What they found was even more disturbing. Atlast's energy dissipation during the maneuver was inconsistent with typical solar heating models. It lost velocity too efficiently, like a craft braking, and yet there were no outgassing events detected. No visible mass ejection, only momentum loss. This wasn't drift, it was navigation. Public reaction was immediate and polarized. Some called it comet paranoia. Others, especially those tracking the coordinated post-perihelion flares, saw confirmation of a Venus transfer theory that ThreeI Atlast was never meant for Earth. It was bypassing us. The hypothesis divided the scientific community. On one side, the statistical improbability camp pointing to the 0.0131% chance of alignment, the flare timing, and the MRO-released vector data. On the other, the traditionalists arguing that even random paths can occasionally look intentional, that humans facing deep space uncertainty often impose design on coincidence. But there was one more variable, and it couldn't be dismissed: the IEWN radar window. Between December 12th and 15th, Earth-based radar arrays had their final clear shot at Atlas just before it disappeared behind Venus. The Yorn International Asteroid Warning Network requested full spectrum tracking, but only partial data was released. The official line: signal degradation due to solar interference. Unofficially, 2 engineers leaked anonymized tracking logs showing a deceleration pattern that ended too abruptly. As if ThreeI Atlast didn't just fade, it stopped. Right at the edge of the Venus corridor, no tail, no heat plume, no exit vector, just silence. The silence of something choosing not to be seen again. And as Earth rotated into night, one final question lingered: not where Atlast was going, but what was already waiting. Every anomaly begs for a theory. But in the case of ThreeI Atlast, each theory spawned even more questions. NASA's formal working group classified its behavior into 5 broad hypotheses: natural sublimation, active propulsion, internal fragmentation, deliberate trajectory steering, and artificial reconnaissance. None explained everything. Some disturbingly explained just enough. The first hypothesis, the most conservative, assumed Atlast was behaving like a conventional comet. Perhaps they said thermal waves from solar heating reached deeper volatile pockets triggering delayed CO2 outbursts. Perhaps the outburst 14 days after perihelion was just a lag. But the data fought back. No model accounted for that timing. No rotational instability occurred. Spectral readings showed the ejected material was purer than expected, lacking dust or organics. There was pressure. There was sudden symmetrical outflow. But it didn't behave like a natural system reaching thermal instability. It behaved like a chamber being vented. Natural, possibly, but highly atypical. The second hypothesis pushed into bolder terrain propulsion. Some orbital analysts began to model Atlas not as a drifting rock, but as an accelerating object. Its motion could not be fully explained by gravitational perturbations or solar pressure. In fact, its acceleration vector was retrograde opposite the solar vector. That shouldn't happen unless thrust is being applied. JPL teams simulated exhaust models, and disturbingly a phased nozzle-like emission matched the observed delta-V profile. But there were no thermal emissions, no spikes in infrared, no radar cross-section anomalies. Whatever might be pushing it, if anything, it was silent, efficient and hidden, and that silence may speak louder than data. The third theory was a compromised internal fragmentation. MRO imaging showed strange albedo shifts on Atlast's surface, as if internal sections were rotating or peeling away. Some suggested this could explain the timing of the outburst. An inner pocket structurally compromised ruptures days after perihelion, but here again the core logic cracked. No significant debris trail was found, no observable spin wobble, no decrease in structural coherence. In fact, Atlast held together better than expected. The theory of partial disintegration raised more questions than it answered. But then came the fourth hypothesis, one that NASA was reluctant to name officially deliberate trajectory steering. After perihelion, Atlast's orbit shifted. Not by much, just a delta V of roughly 6 ms, but enough to alter its path toward Earth's orbital corridor. And that tiny nudge, perfectly timed, made all the difference. The probability of such a maneuver aligning with Venus-Jupiter conjunctions was less than 0.005%. Coincidence, possibly. But it resembled something more calculated than chaotic, a mission profile, a flyby window. Some researchers quietly began calling it the Atlast turn, and finally the most radical idea of all, that ThreeI Atlast was not a comet at all, but an object of artificial origin, perhaps a probe. Its near-spherical shape, post-perihelion lack of tail, controlled trajectory, minimal emissions and improbable alignment echoed the 2017 debates around Oumuamua, but Atlast was stranger. Unlike Oumuamua, it exhibited behaviour, acceleration, brightness fluctuation, structural resilience, rotational stability, and most importantly, intention. No radio signals were detected, but maybe it wasn't transmitting, maybe it was observing. NASA's internal scoring matrix yielded no clear winner. Sublimation earned 55 out of 100, fragmentation 60, propulsion 68, trajectory steering 72, artificial reconnaissance 79, no theory cleared 80, no hypothesis closed the file. As one ESA physicist said off record, if this isn't natural, it's more than a comet. And so we arrive at the heart of the mystery. After 7 months of observation, over 50 institutional analyses, and more than 4 terabytes of high-resolution data, we still do not know what ThreeI Atlast is. Only that it came, that it behaved in ways our physics struggles to explain, that it left no trace of intention, and that it may never return. For all our models and all our eyes on the sky, we are still left with one uncomfortable possibility. Something passed by, something that watched, moved, and vanished, and we weren't ready. We thought we were just observing a comet, a relic, a visitor from the dark outskirts of the solar system moving silently through gravitational tides, passively melting under the sun's gaze. That was the assumption. That was the comfort. But the behaviour of ThreeI Atlast forced us to abandon comfort. It was never about brightness alone. It was about precision. The way Atlast entered the system was elegant, almost too calculated for a chaotic object. Its activation post-perihelion wasn't just mistimed, it was misaligned with everything we know about thermal model spin evolution and internal pressure dynamics. And yet, the data held. When we confirmed the trajectory adjustment, something shifted not just in the math, but in the minds of those studying it. This wasn't a rock reacting, it was a body responding. The implications rippled across institutions Harvard, Caltech, JAXA, ESA, and the Vatican Observatory, quietly submitted internal memos to reclassify Atlas not merely as a comet, but as a non-passive interstellar object. The term sounded vague because vagueness offered shelter from what it might mean if we were witnessing intention. ThreeI Atlast changed the paradigm, not with spectacle, but with subtlety. Not through contact, but behaviour. It never spoke, it never emitted signals. But through mass motion and silence, it asked a question one we weren't prepared to answer. If even 10% of the artificial hypothesis holds, then the implications are seismic. It means there exists a capability somewhere, sometime, to send objects across interstellar space to steer them through solar gravities, and to do so with such finesse that the observers us would barely notice unless we paid attention. And we almost didn't. Atlast may be the proof not of life, but of engineering. Not of civilization, but design. And that is more terrifying, because design implies purpose, and purpose implies observation. If Atlast was watching, then what was it looking for? That is the terror of indirect contact. There was no transmission, but a statement was made. Not in language, but in physics. In trajectory, in survivability, in timing, in silence. And here's the most haunting part. Maybe it wasn't a probe. Maybe it was debris, a shell, a fragment of something larger, or something left behind to decay. In that case, the purpose is not reconnaissance, it's residue. We're not being visited, we're drifting through their ruins. NASA's final consensus report did not declare Atlast artificial, it couldn't. But it included a new clause never used before in official publications' uncharacterized potential activity. That's a euphemism for we don't know, but it doesn't look natural. It forced a change in protocols. Observation windows for near-Sun trajectories were extended. Budget lines for out-of-plane sensors were reopened. The AUN International Asteroid Warning Network added a new category, Class 6, Behavioral Anomaly. A silent revolution began inside the institutions. Atlast became the pivot. But beyond the science, ThreeI Atlast has left us with a deeper discomfort. For centuries we've searched for signals in the noise, looked for biosignatures in exoplanet atmospheres, and dreamed of SETI pings from stars 100 light-years away. And all the while, something smaller, quieter, and more local may have just passed us by. Not with fanfare, but finesse. Not to say hello, but perhaps to remind us we're not alone in this physics. If it was natural, then we've just encountered a comet that breaks multiple laws we thought we understood. If it wasn't, then something is capable of more than we imagine, maneuvering without heat, accelerating without mass loss, and navigating our solar system with the precision of a mission plan. Either answer reshapes astronomy. But perhaps the greatest implication is philosophical. ThreeI Atlast did not change direction when observed. It did not respond to our pings. It did not react when we looked, which means it was never trying to talk to us. We were never the subject, and that changes everything. We're used to thinking of ourselves as the center of curiosity, the listeners, the recipients. But what if we're just background? ThreeI Atlast might not be a messenger. It might be a memory. And if that is true, if we've just passed through the shadow of something greater, older and utterly indifferent, then the real question isn't what it was. The question is, what else have we missed?